This is section 13.5, and we have our last example in our notes, which is example 6, and we're going to determine whether or not the vector f is conservative. So we're going to calculate the curl of f. Okay, I'm going to fill out each of these parts really quick, so I'm going to pause and then come right back. All right, so here's our worked out curl of f, and as you can see, what we get is the 0 vector. I just wanted to make one observation that I think can be really helpful here. If you remember, when we were working with conservative fields in section 13.3, and we were talking about the fundamental theorem of line integrals, we were testing, essentially we were testing if the partial derivative of p with respect to y was equal to the partial derivative of q with respect to x, and that came from a vector f equal to the vector pq. And we said, well, okay, if those two partial derivatives are equal, then we have a conservative field. And not only that, but if we were doing Green's theorem, if those two things were equal, then Green's theorem fails and we can't use it. If you notice, based on our formula for the curl of f in 3 dimensions or in 3 variables, the whole idea of dp dy equal to dq dx is that last component. And so when we were looking at this in section 13.3, we were talking about having just the variables x and y. Now what we're doing is talking about having variables x, y, and z. And so this is essentially the exact same type of test, but now in 3 variables versus 2 variables. We can't just test dp, dy, dq, dx in this type of problem, example 6, because we have too many variables to do that with. But if we were down to just variables of x and y, then kind of we're just sort of basically doing the curl of even a vector of x and y. So anyway, if that's helpful at all, we're just doing this. We're doing what we did in 13.3, just on a larger scale. So anyway, because this vector curl of f is equal to 0, 0, 0, then the vector f is conservative. So what we're going to do in our second part here is we're going to find a function of x, y, and z such that the partial derivative of f is partial derivative of f with respect to x is equal to 2xy, and the partial derivative of f with respect to y is x squared plus 2yz, and the partial derivative of f with respect to z is y squared. So again, we're just looking at the elements of our vector. We're saying that, okay, if it's conservative, then the statement that this vector f is equal to the gradient of f is true, and so therefore it follows that each of these components are partial derivatives of some function that we're going to be able to find. So again, our strategy here is that we start with the first one, 2xy, and we take the antiderivative with respect to x. That's going to be x squared y. Then what we do is we test that against the next partial derivative. So if we're looking at our second partial derivative, x squared plus 2yz, let's see if we get that. So if we take the derivative of what we have right now, we get, with respect to y, we get just simply x squared. And that's good. We have x squared here. But the issue is that we have neglected the rest of this partial derivative. So let's deal with that second part. The antiderivative of 2yz with respect to y is going to be y squared z. Okay, so let's double check the first one again. So if we take the derivative of all of this with respect to x, we get 2xy, everything's good. If we take the derivative with respect to y, we get x squared, and then 2yz, so that's all good. Let's do the third one. So if we take the derivative of all of this with respect to z, we get y squared, and that matches perfectly, which means all we have to do is add a possible constant, and we have a potential function. Okay, that's example 6, and at this point we will move on to section 13.6.